here, and another is talk about human-robot cooperation after Lean. I hope some of the applications I showed will provide a current definition of cooperation. Well, I won't address the dancing context as by scene, but I will talk about clothing, about robots helping humans, helping people to dress or to fold clothes and so on, to do the laundry. First of all, where I work is the Institute of Robotics and Industrial Informatics, which depend on the Council of Scientific Research of Spain and the Polytechnical University of Catalonia. So it's a joint venture. It's a pure research center. We have about 100 people working there, but one of our main task forces are robots. We have leg robots, wheel robots, all sorts of humanoids, small humanoids, bigger ones. But I will talk about robot manipulation. Particularly, where I work is this perception and manipulation lab, where we have 2 one robots. The mouse doesn't work. We have 2 one robots, and also we have more industrial type robots, stable robots, and also haptic devices. And our long-term aim is to work in put robots in human environments, and especially assistive environments. This is the team I work with. I'm very proud of them, and you see that we have very good link with our robots. We are very good friends with them. And starting properly with the subject of my talk, textile objects are all over the place in human environments, and of course their versatile manipulation will open up many possibilities. I mentioned here a few. One is housekeeping and hospital logistics, as I mentioned. Another one is in the clothing business through internet. Some people buy, say, 6 clothes or 6 dresses, and after trying them on, send back 4 of them because they don't want. So they arrive in boxes, and someone has to take them out and hang them on again or fold them. So here it would make a big change to have robots to do that. And also we aim at helping disabled people to dress and recognizing the different levels of disability and helping them to put clothes on, a jacket or whatever. This clothing handling poses several challenges for learning algorithms. I mentioned here some. We try to somehow build building blocks to get an end-to-end application. So you see here we have challenges in vision, in human-robot cooperation, in skill tuning. Safety is a major issue in this type of applications, and also to be able to develop tasks within tasks, it is important to have task planning abilities. So starting in the first challenge, we have performed garment recognition and pose estimation for informing grasping of clothing. What do I mean by informing grasping? Usually when you take the clothes from the washing machine, say, they come like this, and many people address the problem of separating them and folding them and putting them in the cupboard again by separating and then re-grasping the cloth many times in order to get to a standard configuration, say to put it flat on the table and then fold. We plan to do it differently and exploit the very sophisticated algorithms developed in the computer science community, or computer vision community, in order to pick the clothes by a place that permits performing the task. For instance, if we like to hang the cloth, then we like to pick it up by the collar, etc. So determining grasping points that are suitable to perform a given task. Now I will show you how we define where a good given task is. We have devised a data set of clothing which is publicly available and that other groups have used already, in which we have, I think it's 6 types of clothing, pants, dresses, shirts, t-shirts, and we have collected color, depth, and the template for background subtraction for each of them. Moreover, we have annotated the different parts, the collar, the hemlines, the hips, etc. on them. And the idea is that once a task is defined, say hanging, for instance, we apply a back-of-words algorithm to learn the particular characteristics of colors.
Annotation by hand?
Yes, the annotation is by hand.
By hand.
Yeah, has been done by hand. Well, with a bit of help, because I will explain it later, but endlessly by hand. Then we apply the back-of-words algorithm in order to compute a map of likelihood of where the color lies. And well, we define a bounding box around it, and then we like to be more precise and pick it by the label of the color, not just anywhere. And for this, we have devised a 3D descriptor, which is based on the local arrangement of the normals of the surface. Because the label has some 3D shape. Well, I won't go into details on this, but then for different pieces of clothing, we can determine first the bounding box of the color, and afterwards a grasping point of the label. And we get 82% success. The same 3D descriptor we have applied to garment recognition and classification. And we have compared with classical 3D descriptors like SHOT and FH. You see the one that gets the best results is this one, although our descriptor is quite competitive, and even in some particular cases it gets better. But what is important is that it is 2 orders of magnitude faster, because it relies only on depth information. Well, this is one building block towards this growth handling. The next thing I'm going to show is human-robot collaboration from demonstrations. In this case, I will show first an application with a rigid object. The purpose here is to assemble this IKEA table between the human and the robot. So to do that, first this will be acting as a human, and this will be a teacher that will be holding the robot so as to show the right behavior. And what is intended is that the robot acts as a third hand, say. So this person wants to assemble this table, so this part of the table should be compliant while he is moving it around to put it in a comfortable position for him. And then when he tries to screw the leg, then the robot should help stiff the base of the table. So there is a video here which will show. You see now is the demonstrator phase in which he is holding the robot to give it the right behavior, and now it goes to stiff behavior while it is screwing. Note that it is based on both vision, because here there are some sensors for the vision, and also on haptics. Now it is the robot is behaving as expected. It is stiff while the human is screwing the leg. But if the leg is screwed in a bad position, let's say in the middle of the table, then the robot doesn't recognize it that it has to be stiff, so it behaves compliantly. And the same if the leg is upside down, like here. So this provides us with the first demonstration of what the intended behavior by the robot should be. Usually this type of behavior needs to be tuned in order to be more ergonomic for the robot or improve certain cost function. And this skill tuning is usually done through reinforcement. And I will show this in the context of helping to dress. For these skills, we are using DMPs, dynamic motor primitives. And the idea is that there is a first demonstration like we had before. Then this is projected into a latent space with less parameters, because reinforcement learning has this problem that if the search space is very large, then it takes a lot of time. So we project onto a latent space with fewer parameters, and then we optimize a certain cost function. Well, this is the usual formula for the DMP. This is the excitation function. And what has to be learned are these parameters that are weights on Gaussian functions. So here you will see that from a first demonstration, that is very bad. You see it's putting a scarf on a mannequin, but the first is not really meeting the goal. But after we have a cost function, because we have a Kinect on the top that measures whether the scarf is on the mannequin. After 10 rollouts, you see that it's improved quite a lot. And after 20, it improves even better. Well, this is just to show that since reinforcement learning, as I said, is quite time-consuming, we have implemented two ways to speed it up. One is to search only along relevant directions, parametric space, using PCA. And the other is to introduce a second layer of Gaussians. With a first layer of Gaussians, we encode the initial demonstration. And then this fine tuning is done just in the second layer of Gaussians. And you see that this leads to a quite good behavior improvement over not using these speed-up procedures. Next, as I said, safety in this helping to dress application is crucial. In this video, I will show here in the left panel, there will be the initial demonstration. Here, the autonomous dressing by the robot. And in this black spot, you will see the most interesting behavior because it will put the scarf on a person. And the thing is that this person can distort the behavior of the robot, the trajectory, quite strongly, as you see. and still the robot behaves nicely and perseverates in finishing you see, I play it again. I'm sorry. I play it again because, you see, this is the PhD student that is doing the work, and he's the only one that risks his neck to be placed here. We couldn't get anyone else. But you see that it does well. This is, we have incorporated a dynamic, a very precise dynamic model of the one robot, including frictions, for instance, including every small thing, in order to control that it will behave as nicely. So, through learning by demonstration, you can teach a given task to a robot. But when the robot faces a slightly different context or a slightly different task, then some symbolic understanding of what is going on is needed, not just a reproduction of a objective. So another building block in our research program, say, is to carry out task planning for several applications. One is cleaning surfaces with the help of a cloth. You see here that there are some dirt in a surface, and the thing is that this robot is held in a cloth, and every time it grabs the cloth differently. So the outcome of the actions differs. Here, for instance, you see that it will miss some of the dirt, and it will have to come back to get it. So we plan this type of task using probabilistic action rules, meaning that there are different possible outcomes, each with a probability. And as long as the behavior is going on, the planner learns these probabilities for the specific context. Within a European project called Intelac, we have tried to go one step further by showing by starting with a planner that knows absolutely nothing, has no actions, anything. And then the operator shows an initial demonstration from which the system learns some rules, some assembly rules. The benchmark is this Cranfield assembly, which is quite common from the 80s. It entails putting several bolts in the right places, fixing holes, and then some of the blades on top, etc. The thing is that there are some precedence constraints which are not explicitly taught to the system that should be learned. So there is an initial demonstration by an operator here using a virtual reality system, but we had also the setting to do it in real. And at the first stage, it learns the different actions and the rule probabilities of the different outcomes. Then, in these human environments in which we tend to work, we don't want the system to take long time to complete the task if a human is in hand and can supply the needed information. So when some situation like this one arises, in which this new situation, this separator is called, is placed before the bolts that should be in, the system doesn't know what to do. In our system, this is marked with a red semaphore. When it doesn't know what to do, it asks for teacher help. Then the teacher just tells a new action. A new action is separator removal in this case. So the system knows that when it faces, again, this situation, it has to remove this separator. and from here it knows how to proceed as before. So when this extreme situation arrives again, the system autonomously knows what to do. You see here that it shows that the action removes separator. But we think it is important to go one step further again and guide the teacher, telling him what information the system is missing. Because sometimes the system stops because there is no valid plan, but the operator, for instance, has several options. Assemble this or this, and doesn't really know what is troubling the system, what the failure is. So we have implemented a system to explain what is the failure, and we have based this on what is called excuses in the probabilistic planning domain in artificial intelligence, which are that the system informs of minimal changes in the state that would make the problem solvable. So if you put me in this position, I know what to do. So the human operator then knows what has to instruct the system on. And another important thing is not to make extensive use of the teacher, so minimize teacher interactions. And this is attained by defining sub-goals. If there are chunks of the task that the robot knows how to do, then encapsulate them. This will appear in the special issue of the Artificial Intelligence Journal on AI and Robotics. I think this is what I wanted to say. Thank you.
So we have time for one question while our next speaker is here.
So I was thinking that whenever I manipulate clothing, use two hands. It's actually pretty hard to put a scarf around somebody's sleeve. Have you thought about using two hands, or is the problem becoming harder because the robot has to do everything with one hand?
Well, we started with the simplest problem, is of putting a scarf on. We are now working on putting a jacket, and we are using the two one arms. And the interesting thing is that we are trying to optimize the configuration of the two arms. Since we don't have a torso with the two arms in a humanoid configuration, we have two single arms. We can place them in positions that are more amenable to the task we like to perform. So, for instance, one on top and one on, it depends on the task. But we are experimenting with the, we are not constrained to the bimanual humanoid